Hello everybody, and welcome to the next video in our GManager Quant series. This video will be the second of our two-part look at number properties. Now, just to be clear, because different companies define number properties in different ways, when I talk about number properties, what I mean is things like lowest common multiple, greatest common factor, looking at factors, divisibility, remainders, powers of 10, and then maybe some miscellaneous questions that could fit under some algebra, sort of looking at whether a number is odd or even, or looking at whether a number is an integer. Now, in the last video, we took a closer look at greatest common factor, lowest common multiple, divisibility. But really, that video, the first one, was all about looking at things you could formalize in number properties. This video, well, if we're looking at the topics that we're going to see, we'll take a look at some odd even questions. We're going to deal with loads of remainders, and we're going to be looking at things involving powers of 10. But this video is more about the pattern spotting side of things. Sometimes in number properties, you can formalize a method, or you can use some sort of quasi-algebra sort of algebra to answer a question. And we dealt with that in the first video. This video is for the questions when you're standing there and it feels like you're standing there with a hammer, a bunch of nails, a load of jello, and you've got to nail that jello to the wall. You just don't know where to begin with it. The question almost evades you, and it's how to spot the pattern that's going to help you here. And then also we've got this bit about using what we might call the stupid method. We hinted at that in the first video, but we're going to take a closer look at what I mean by that as we go through some of the questions today. Now, this video is for you. I mean, obviously, if you can't spot the patterns in a number properties question, we're going to have a few things for you. But also, if you feel you're rigidly tied to a method, if you've just sat down and you know all the formulas and processes, if you've sat down and memorized a bunch of facts about numbers or memorized the processes, then we're going to be picking apart these questions, and we'll certainly have a few things for you. In particular, if you struggle to see a pattern in the question, this is going to be the big thing today. Now, I've got 8 questions for you, and in a second, we'll put them up on the screen. We'll give you a couple of minutes to take a look at the first one, and then we'll go through it together. You could probably rate the difficulty of this video somewhere between the moderate to difficult side of things. Now, that really depends on whether you can see the pattern in a question. It's actually very hard to nail down the difficulty rating of these questions, because if you can spot the pattern, if you see the trick, these questions are very easy. If you can't, this is going to feel like you're going to be bashing your face off the wall again and again and again as you try and unpick it. So I'll do what I can to judge the difficulty rating of the questions as we go through. But as an overall thing, I think you could say somewhere in the moderate to challenging region. We're not going to have anything that'll melt your face off, but it's not going to be that easy either. All right, so without any further ado, I will get the first question up on the screen. We'll give you a couple of minutes to take a look at it, and we'll see you back here to go through it together. Okay, if you've watched any of our videos before, you'll know the pattern by now. If you need a little more time to take a look at this one, feel free to pause the video here. We'll still be here when you're done. But I'm going to take the question away now so that we can take a closer look at this one together. All right, so this question, as I said before, I'm going to try and give you an idea about the difficulty levels here. That this one, if you can spot the pattern, it's very easy. If you can't spot the pattern, you're going to be here for an awful long time. In terms of your overall score, it's probably going to be somewhere in the middle. This is not a particularly difficult question, but it's a nice one to begin with. Now, as I said at the start, this is all about patterns. We want to know the remainder when 3 to the 37 is divided by 10. Or in other words, we want to know the units digit of 3 to the power of 37. Now, obviously, I do not want to be sitting there calculating this. Even if I had a calculator, it's very unlikely it's going to be able to have enough characters on the screen to show me this. This number is going to be enormous, so we need another way around it. And there's a pattern that we can follow here. So if I set up a bit of a table to begin with, if we just call this column X, and I have 1, 2, 3, 4, and we'll keep this going for a while. And this is, in this column, I'm going to have the units digit of 3 to the power of X. Now, 3 to the power of 1 is just 3, so we can stick that number in there. 3 squared is 9, so we get the units digit there. 3 cubed, 27. But all I'm interested in is the units digit. Reason for that is because as I multiply my way up this column, I don't want to keep doing powers of 3. The numbers get big, they get horrible. I don't want to be doing that sort of calculation. What I can say is the next number, 3 to the power of 4. Now, probably many of you watching this video have done enough GMAT stuff. You just know that that's going to be 81. But I don't need to do 27 times 3 to get 81 to get the units digit. I could just do 7 times 3. That'll give me 21. Take the units digit of that 21 and I'll get 1. And then equally, 3 to the power of 5, well, that's 243, but I don't want to do that sort of big calculation. I could just take this 1, the units digit that we had, and times that by 3. And I can keep this pattern going, working my way down. So 3 times 3 is 9, 9 times 3 is 27. I just want the units digit, so it's 7. 7 times 3 is 21. I just want the units digit, so it's 1, 3, 9. And we could keep this list going. We could keep it going all the way to 3 to the 37. But I don't want to. I don't want to go that far. What I hope you've spotted by now is there's a pattern, there's a repeating pattern in the units digits as we work our way down the board that repeats every 4 units. The units digit of 3 to the power of something repeats 3971, 3971, 3971. And so really the question becomes, well, 3 to the 37, how many times do I go round this pattern? Well, it repeats every 4, and we could say that that is 3 to the power of 36 plus 1, 3 to the power of 37, 36 plus 1, which is 3 to the power of 9 times 4 plus 1. Or in other words, I'm going to go around this cycle 9 times, and then 1 more. So 3 to the power of 30, well, 3 to the power of 4 would have a units digit of 1. You go around the cycle again. 3 to the power of 8 would have a units digit of 1. You keep going around. 3 to the power of 36 would have a units digit of 1. 3 to the power of 37 would be 1 further on. So it's going to have a units digit of 3. And our answer here is going to be B. Now, this way of spotting the pattern will work for other numbers as well. If you had, what's the remainder when 2 to the power of 53 is divided by 10? Again, you get that same pattern, multiply down by 2. In that case, it actually will repeat every 4, and then you can follow the same process and find the number there. This will repeat for the powers of, 7 to the power of 97. The units digit of that, again, same process. So you just find the units digit, spot the pattern, and build up this process, and you can find the units digit of any number, really, if you wanted to go for it. All right, so there's our first question. I will get this out of the way and get the second one up on the screen for you now, and we'll see you back here in a couple of minutes' time. Okay, now's your chance to pause the video if you need a little more time on this one. We're going to take the question away so that we can do this one together on the board. Now, this is another middle-of-the-road question. We're really still just warming up here, so there's nothing hopefully overly challenging about this. Again, it's all in the pattern. If you can spot the pattern, you can sail through this question with little difficulty. If you can't, you're going to be here for a while. All right, so we're told here that we've got a delivery of fewer than 100 boxes, and we want to know how many boxes were in the delivery. So I'm going to, because we're going to need a little bit of algebra here, I'm going to put a variable on this, and I'm going to say that my number of boxes is going to be n, and the question I'm looking to answer is, well, what is n? That's about all I can take from the start of the information. I can say n that's less than 100, but that's about as far as I can go with it. Now, data sufficiency question, so I'll get the AD over BCE set up ready, and then taking a look at piece of information number 1. So when arranged in stacks of 9, there are 4 boxes left over. So I'm going to have boxes in piles of 9, so 9 here, 9 here, 9 here, however many stacks there are, and I'm going to have 4 left over. So I could say that would give me, well, stacks of 9. Don't know how many stacks there are, but they're in stacks of 9, and there will be 4 left over. Now, I don't know what x is. Can't tell how many stacks of 9 there are from that information, so I can't put a number on n. It could be a range of different things. So piece of information number 1 is not sufficient, and I'll cross out A and D. I can do a very similar thing with piece of information number 2. Again, stacks of 7. So I'll have 7 here, 7 here, 7 here, 7 here. Don't know how many stacks of 7 there are, but there's going to be 5 left over. Now, in that case, I could say that that's going to be 7y plus 5. Now, I'm being very careful here to use a different letter. The idea that there is not going to be the same number of stacks, or it's very unlikely there's going to be the same number of stacks when I stack them in stacks of 9 and when I line them up in stacks of 7. So I've got to use a different letter there so that I don't get confused by what's going on. But in a similar way to piece of information number 1, I don't know how many stacks of 7 there are going to be, so number 2 is not sufficient. Now, putting them together to check whether this is going to be C or E, one thing you might do is look at these and go, okay, well, I've got 2 equations, but I've got 3 unknowns, n, x, and y. Well, I can't solve 3 equations if I've got 2 unknowns, so this is going to be insufficient. And this is where that stupid method that we spoke about up at the start of the video came in. That, yeah, algebraically, I can't solve these. There's no way I can do this. But we've got a couple of limitations on the problem here. We know that the number of boxes has to be an integer here because we're talking about whole numbers of boxes. And we're told that the number is less than 100. So what I could do was just start listing numbers out and see where I get to. Now, this might sound like it's going to take a long time, but we've lined this question up. So this is probably longer than anything the GMAT's going to ask you to do. And as you can hopefully see in a second, it's not going to take that long to see if we've got an answer or not, see whether both of them together is sufficient. So 9x plus 4 here, starting to list things out. If x is, if x is 0, then we've got 4 boxes. If x is 1, we've got 13 boxes. X is 2, we've got 22 boxes, and so on. And you're just adding 9 here, and we can very quickly build up a list. And the next one you'd get would be 103, and that's too big because we know n's less than 100. Now, second piece of information, all we need to do is, again, very quickly rattle off a list and just check, is there any overlap? If there's 1 number in both lists, great, it's sufficient. If there's 2 numbers in both lists, it really isn't sufficient. So 7y plus 5, if y is 0, then we'd have 5. If y was 1, we'd have 12. If y was 2, we'd have 19. And again, you can very quickly build up a list. Now, there is 40 in both lists, but there is no other number that appears in both lists. So 40 is the only option for the number of boxes, which means that we can figure out n from the information together, and we can say that this is sufficient, so the answer here is C. Now, as I said, that feels like it takes quite a long time to do, but as I said there, that we've set this question up so that this list is probably longer than anything you're going to see on the GMAT. And the difference between here is just 9. You just in case of just quickly rattle off the numbers, you can be very accurate with it, and you can see that there's going to be some overlap there, whereas you just can't solve the algebra. There's just no way of doing it. So in this way, the stupid way, they're just listing numbers rather than actually using algebraic method is the only way of answering this question. All right, that's all I've got for you on this one. So we'll get this question out of the way and we'll see you back here in a couple of minutes' time for the next question. Okay, I hope you've had enough time to look at this one. If not, now's your chance to pause it before we take it away and take a closer look at it together. All right, so this is another one that's sort of towards the easier end of the difficulty scale. This is another one, if you spot the pattern, you're going to be through this one very quickly. But if you don't, then it's going to be a big challenge to just sit and try and rotate this dial around 7,785 degrees time. So let's go see if we can take a way of doing this one a little bit more quickly. To begin with, we know the dial is split into equal side segments. So let's go and figure out how big each segment is. Now, there are 360 degrees in one full turn of that circle. The dial is split into 8 segments. So each segment's going to be 45 degrees there, which we can put onto our diagram there. So each segment, we know that they're all the same, 45 degrees each. Now we want to turn 7,785 degrees. Now I don't want to be standing there going, right, 45, 45, 45, and adding all that up until it hits 7,785, and then I know where I am. Again, going to take forever. We don't have that much time here. We need a shortcut. What I can say is by turning 360 degrees, my dial's going to be exactly back where it started. Now, if I did that twice, so I used up 720 degrees, again, the dial's going to be right back where it started at number 5. I want to get to 7,785 degrees. So if I times this by 10, or in other words, if I rotated the dial 20 times back to where it started, I've used up 7,200 degrees. Now, if I take 7,200 away from 7,785, I'm left with 585 degrees. So I've got 585 degrees left to deal with. Because that's bigger than 360, I'll turn it around again. Another full circle. And the red line's going to be back pointing at number 5. If I do that subtraction, I've got 225 degrees left to play with. Now we're less than 360. I know I've got less than one circle to go. We're nearly there. Now, if I rotate it 180 degrees, I know that it's going to be pointing in exactly the opposite direction to where it's pointing now. So rather than pointing at the 5, it's going to be pointing at the 1. So take away another 180 degrees. I've got 45 degrees left to deal with. Each section is 45 degrees. So if I had the arrow, we've moved it. We're down at this final stage. I've got to move it 45 more degrees. It's now pointing towards the 1. If I move it 45 degrees clockwise, I know that's a move that's big enough to leave the 1, but not big enough to go right through the 2 into the 3, because that section is 45 degrees itself. Which means that if I move 7,785 degrees, I'm going to do a load of turns. Doesn't matter how many. Then I'm going to do a half turn to point towards 1. 45 degrees more, I'm going to be pointing at 2. And so my answer here will be B. The key to this question is spotting that moving 360 degrees is not going to change where this is pointing. The dial would still be pointing at the 5 no matter how many 360-degree turns you do. That means you can reduce 7,785 very quickly down to a number that's manageable. Again, if you spot the pattern, these questions aren't that bad, but if you don't, you're really going to struggle with them, and that's what we're looking at today. What should you look for in a question that helps you get through them? All right, I hope that question made sense. We're going to get this one out the way, and I will see you back here in a couple of minutes' time to look at the next one. Okay, as ever, pause it now if you need more time to look at this one. I'm going to take the question away so that we can go through the solution. All right, so yeah, scenario here, Alejandro's going to a shop. He's going to buy some lollipops, chocolate bars. Sounds like a great shopping trip. And we want to know how many chocolate bars he bought. Now, this question, we're beginning to just tweak the difficulty level up a little bit. This question would challenge quite a few of our students just because they would struggle or might struggle to see the pattern going on in it. Now, as I say, we want to know how many chocolate bars he bought. Let's just say that, put some variables on this. So number of chocolate bars is going to be C, and the number of lollipops is going to be L. And the question we're asking is what's C? Right. Now, number one, we can deal with very quickly. He spent $235 in total. Great. I don't know what the cost of each lollipop was, what chocolate bar it was. I don't know how many of each. I've got very little information other than he bought two things and spent $235. I don't know how much of each one that is. So A and D can go. Second piece of information, the lollipops cost 19 cents each and the chocolate bars cost 35 cents each. Okay, looking at number two by itself, again, he could have spent $100 on this. He could have spent $1,000 on this if he was going for a real sugar fest there. We just don't know. So by itself, yeah, B's not enough. All right, putting them together, again, we're checking between C and E here. Now, if I put them together, well, then I've got something I can create an equation out of. So the lollipops, L, so we could say that 19 cents times L, or 0.19 times L, plus 0.35 times C equals 235. Now, just to make this simpler, I'm going to multiply everything by 100, and we get an equation. Now, lots of people at this stage would go, right, I've got one equation, I've got two unknowns. That's clearly insufficient. I clearly can't solve it. But there's an extra piece of information implied here that means that we might be able to do something with it. Alejandro can only buy an integer number of chocolate bars and an integer number of lollipops. These can't be fractions. L and C cannot be fractions. They can only be whole numbers. They can only be positive whole numbers. And we can play on this information. Further, we've got the way that these numbers are set up here. The answer here, multiple of 5. 235 is a multiple of 5. 35 times something. So whatever the chocolate bar, the total value of the chocolate bars that we're dealing with, it's going to end in a 5 or a 0. 19, this is a prime number. This is the key and the way in. So whatever we get, the value of the lollipops plus the value of the chocolate bars must add up to some multiple of 5. Because the 35 here times the chocolate bar, that will definitely end in a 0 or a 5. Well, that means that the total value of the lollipops also must end in a 0 or a 5 in order for us to end up with the total price of $2.35. Now, there's only so many options we can have here. If Alejandro goes and buys 5 lollipops, well, then he spent 95 cents on lollipops. That's one option. If he buys 10 of them, well, then he spent $1.90 on lollipops. If he buys 15 of them, well, then he'd have spent $2.85, and that's too big already, so he can't have done that. So that's not an option. In order to make this equation work, he either bought 5 lollipops or he bought 10 lollipops. Now, I know we're looking for the number of chocolate bars here, but this gives us a way in. If he bought 10 lollipops, well, then we can add on numbers of chocolate bars to see if that hits $2.35. So if he bought 1 chocolate bar, well, that would be $2.25. If we added on another 35, well, now we're up at $2.60. There is no way of making that scenario equal the $2.35 that we needed. So that's not an option. All right, final check. We're just going to add on 35 cents onto the 95 and see if we hit that $2.35. So 95 plus 35 once would give us $1.30. Add on another $1.65. We're getting closer. We're at $2. And we're there. It hit the $2.35 that we were looking for. And we can tell from that Alejandro bought 4 chocolate bars. So we can say that the information from number 1 and number 2 together is sufficient. And so our answer is C. Now, again, this is a very long-winded way of doing it, but we need to go through the full explanation to justify why we're going about this. If you were doing this yourself, you could just take this equation and run through this algebra very quickly to confirm that you get one answer when the number of lollipops is 5 and the number of chocolate bars is 4. The key to this question is to know that the number of chocolate bars, the number of lollipops Alejandro can buy are positive integers, because that gives you a limitation on the number of scenarios you can deal with. And it means that even though we've got 2 unknowns in one equation, we can go and find a unique solution, which means that information is sufficient. As I say, we're beginning to take the difficulty level up here. But again, the algebra is not that hard. If you can spot these pieces of information in the question, then you've got your way in and you can hopefully answer these questions. All right, I'll get this one out the way and we'll see you back here in a couple of minutes' time after the next one. Okay, folks, now's the chance to pause it if you need a little more time here. I'm going to take the question away so that we can take a closer look. Now, again, this is another one where the difficulty rating is actually very hard to put your hands on here. I would hope that most people sort of mid-40s and up would be fairly comfortable here. But this is another one where if you can't spot the pattern, this is going to be a very difficult way into the question. First of all, let's take a look at what we're actually being asked for. So we want the probability that a number will be divisible by 8. First up, let's actually go and take a look at what does it mean for a number to be divisible by 8. We've gone into quite a lot of detail with this in the first video, so I'm not going to take my time here. If you want to see this in action repeatedly, see it gone into detail, go take a look at that first number properties video. For here, if I had a number, let's just call it x, if it was divisible by 8, then x divided by 8 would equal just some integer. Some whole number, don't know what it is. If x was 16, a would be 2. If x was 24, a would be 3. If x is divisible by 8, I'll get some integer out of that, which means that x is 8 times that integer. And if I prime factorize that, it would be 2 cubed times a. For a number to be divisible by 8, it needs 3 2's in its prime factorization. So if you want to check whether a number will be divisible by another number, it's what is in the prime factorization, and can you tell whether that number's in there? Now, in this question, there's a bit of a pattern going on here. We've got n times n plus 2 for all the numbers from 1 to 1,000. Again, I don't want to check every one. I want to find a way of seeing a pattern and seeing if I can shortcut this. So what I've done here is I've built a table over on this side of the board here. Again, if you're doing this question yourself, you probably don't need to go through all this process, but so that everyone can understand what's going on, I'm going to break this question down a little bit more than I might otherwise do. Now, I've got values of n here from 1 to 10, values of n plus 2 from, starting from 3 going up to 12. This column's 2 bigger than the first column, and in this third column, we're going to multiply those two together and get the result here. So we'd end up with 3, 8, 15, 24, 35, 48, 63, 80, 99, and 120. And we need to, if we know the 8 times table, we're able to see that, first of all, 3, not there. 8, yes, that's in. 15, we can definitely say all the odd numbers are not multiples of 3. 24 is, 48 is 6 times a, 80 is in, 120 is in. And you can hopefully begin to see the pattern here, that it's just going no, yes, no, yes, no, yes, no, yes. Now, the question you might ask is, how do we know that pattern's going to continue? And so what we can do is begin to break down the numbers that are here. As I said before, we need to know that there are 3 2's in any of these numbers. Now, in this top line, no, there's no 2's at all. They're both odd numbers. But in this second line, I've got 1 2 there, and I've got 2 2's if I prime factorize 4. Second line, we can ignore the odd numbers because they're not going to be involved. But then this third line, I've got 2 2's and a 4, and 1 2 and a 6. I've got 1 2 and a 6. In this case, I've got 3 2's and an 8. I only need 3 of them overall, so that's definitely going to work. Next line, I've got 3 2's there. I've got 1 2, so I've got 4, which is more than I need. But coming down 10 and 12, 10, I've got 1 2 in the prime factorization, and 12, I've got 2. So in total, I've definitely got the 3 2's I need. What we're doing here is n plus 2. I've got 2 consecutive even numbers. In any 2 consecutive even numbers, one of them is going to be a multiple of 2. One of them is going to be a multiple of 4. Now, I know the multiple of 4 is also a multiple of 2, but you see the point. One of them is going to be a multiple of 2 and not a multiple of 4. The other one's going to be a multiple of 4. So in that case, the first one would have 1 2 at its prime factorization. The second one would have 2 2's. I get the 3 2's I need. I know that every other entrance in this pattern is going to give me a multiple of 8. And so that because it's every other number, half the numbers from 1 to 1,000 are going to be a multiple of 8 in this pattern. Probability is going to be a half, and my answer is C. Now, this question style is quite common on the GMAT, and it's just about looking for what am I looking to divide by, and then what's the pattern. It might be n plus 1 divisible by 4. And again, it's that same idea. Build a table up, check the answers, and just confirm for yourself that that pattern is going to continue. If you can spot the pattern quickly, then these questions do fall out very easily. All right, that's all I've got for you on this question. As I said, the difficulty level is going to begin to ramp up as we get into the final 3 questions. These are ones that, if you're not in the mid to high 40s already, you'll probably find a little bit challenging. But again, as with all of these, you don't need to get every single question right in order to get even up into the 48, 49, 50 region. All right, I'll get the next question up on the screen, and I'll see you back here in a couple of minutes' time. Okay, now's the chance to pause it if you want a little more time to work on this one. But let me take the question away so that we can look at this one in more detail. So when you're looking for terminating decimals here, or if we were looking for numbers of trailing zeros at a big number, the thing to remember is that you're looking for 2s and 5s together. Because if you put a 2 and a 5 together, then we get a 10, powers of 10, and powers of 10 just move the decimal point one way or the other. They'll give you more or fewer zeros in a huge, great big number, or they're going to give us more zeros or fewer zeros after the decimal point in a small number, in a terminating decimal like this. So the key with this question is I'm going to take the start, take the fraction, take the numbers on the bottom, and try and get as many 10s as I can, and then I'm going to see what's left. Now I've got 4 to the 5 times 5 to the 16, but I could rewrite 4 as 2 squared. So 2 squared to the power of 5 means that I could rewrite that whole fraction as 2 to the power of 10 times 5 to the 16. Now I could take that 5 to the 16 and split that into 5 to the 10 times 5 to the 6. Or in other words, I've got 2 to the 10 times 5 to the 10. I could have that. I'll take the 5 to the 6 out the way for the moment and have that as 2 times 5 to the 10. Or in other words, I've got 1 over 5 to the 6 times 10 to the power of 10. Now, the 10 to the power of 10, I can just ignore for the purposes of this question. What I'm looking for is a decimal. I'm looking for the numbers in the decimal. That 10 is just going to move the decimal point one way or the other. It's going to give me more or fewer zeros in it. It's not going to be involved in the number within that decimal. So I'm going to focus on this 5 here. Now I'll rewrite this as 1 over 5 to the 6 times 1 over 10 to the 10, and we'll ignore that for the moment. I could rewrite this 1 over 5 to the 6 as 2 over 10 to the 6. And I've got more 10s here that I can not worry about. I can push them out the way and not deal with them. So yeah, I could write this whole thing as 2 to the 6 over 10 to the 6 times 1 over 10 to the 10, or rewriting this as 2 to the 6 over 10 to the 16. So as we said before, this 10 to the 16, all that's going to do is give me more zero. The bigger that number gets, the more zeros I'm going to have before my terminal decimal starts. The bit that I'm really interested in for this question is this 2 to the 6 on the top row. Now, multiplying up powers of 2, that is 64 over 10 to the 16. Or in other words, writing this as a decimal, it's going to be 0 point, a bunch of zeros, and then 64 at the end. Or in other words, I'm going to have, how many non-zero digits will D have? Well, 2. So the answer there is B. So as I said, in these questions where it's asking you about the number of non-zero digits in a terminating decimal, or even if it's asking something about the number of trailing zeros in a very large number, what you're looking to do is isolate powers of 10 and kind of get them out the way. They're going to be helpful in the question, but that leaves you to play with the other part of the question that will give you the number in this terminating decimal, or the number at the start of a large number with lots of trailing zeros. If you can isolate those powers of 10, now you've got a way into these questions. All right, I will get this question out the way. We'll give you a couple of minutes to take a look at the next one, and I'll see you back here soon. Okay, I hope you've had enough time to take a look at this one. If not, now's your chance to pause it before I take it away. All right. So as we get into the final two questions, these are beginning to get challenging. These are beginning to get tough. I wouldn't be surprised if this caused you some problems, unless you're sort of in the high 40s already. There's a few clues in the wording of the question, and if we've picked up anything along the way in this video and you've cracked it when you wouldn't have been able to before, that's fantastic. If not, let's go take a look at what those clues are so that you'll be able to crack this sort of question in future. Right, so we're given some information before we get going. M and n are positive integers. Okay, that's going to be helpful to begin with. M plus n and m over n are both even numbers. Okay, let's go and use that and see what we can find out about m and n individually. So if m plus n, I'm going to look at that one first. M plus n is even. Right, so two numbers added together and they're going to be an even number, in which case that what we can say is either both m and n are even, something like 2 plus 4 is 6, or m and n are both odd, 3 plus 5 equals 8, which is even. So we know that either they're both odd or they're both even. If we could tell one way or the other, that'd be great, but we can't at the moment. That's all we can say from that first piece of information. Next bit, we're told m over n is even. Now I'm going to represent that as m over n equals 2 times something. M over n is, 2k. I don't know what k is, but that just represents some even number. Now I can take that and rearrange it. So m, multiplying both sides by n, m is 2kn. Well, because m is 2 times something, don't know what kn is, but m is 2 times that, that means that m is even. Now, if we go back to the first piece of information, well, that means that top line's not possible because they were either both even or both odd. So because I know m is even, I also know n is even. Now I can take what I've done here and say, well, okay, m is 2 times k, but I could rewrite n, because I know it's even, as 2 times something else. So m is actually 4 times something. I don't really care what KL is. I'm just interested in knowing that m is 4 times something. So I know that n is even. I know that m is in the 4 times table somewhere. And we're going to go and use that information to get into some of these answer choices. All right, so the question here is, which of the following cannot be an even integer? So first one, if we look at A, m plus n over 2, that's the same as saying m over 2 plus n over 2. I could split that fraction up some way. Now, we know that m is in the 4 times table. So in other words, m divided by 2, well, that's going to be an even number anyway. N over 2, I know it's even, but I don't know much more than that. It could be, this could be even, n over 2 could be even, or it could be odd. In other words, I don't know. So if I'm saying which of the following cannot be an even integer, well, if n over 2 is even, then m over 2 plus n over 2 would give me an even number. So this first one, A, can be even. So it can be, the answer can't be A. Second one, m over 2. Well, as we said, m is in the 4 times table. So if we divide m by 2, we're still going to have an even number. So it definitely can't be B. Now for C, n plus 2 over 2. As I said, this is another one we can split apart. N over 2 plus and 2 divided by 2 would be 1. So if n over 2 is even, then the even number plus 1 would be odd. If n over 2 is odd, then plus 1 would be even. As we said when we looked today, I can't tell. I can't tell one way or the other. N over 2 could be even or it could be odd. So adding 1 on, I could get an even number. I could get an odd number. So I can't say that C cannot be even. So it can't be C. Now with D, m plus 4 over 2, or in other words, m over 2 plus 2. Now, as we said before, m over 2, well, that must be even because m's in the 4 times table. You divide something in the 4 times table by 2, you're still going to get an even number. So that's even. We're going to add on an even number. In total, we're going to get an even number. So if we're saying which of the following cannot be even, well, it's not going to be D because that one must be even. All right, we've crossed 4 answers out. We've got to hope that E is going to turn out to be, it must be odd. Well, again, splitting this fraction up, m over 2 plus 6 over 2, or m over 2 plus 3. Now, we've said several times now, m over 2 must be even. 3, well, that's an odd number. Even plus an odd number is always an odd number. So this one must be an odd number, or in other words, it cannot be even. And so E is going to be our answer here. Now, this question, again, if you can see the way in, the actual logic behind it's not that hard. The key with this question is to get through this set of this bit of work so that you know that, well, they're both even numbers, but further, you know that m is a multiple of 4. If you can see that, that guarantees you that m will be even, which is what you need, certainly when you get to the final stage here. Now, I'm going to get the last question up on the board for you just now. Again, this is going to be challenging if you're not already in the high 40s. But again, there's a way of seeing this question. If you can spot the pattern, this question is not that hard. So I'm going to give you a couple of minutes to take a look at this one, and we'll get back together to finish this off soon. Okay, for the last time today, if you need a little more time to take a look at this one, now's your chance to pause it before I take the question away so that we can wrap this one up together. All right, so as I said before, that we're now getting to the difficult questions. If you manage to get through this one, well done. This is not easy. If you struggle with it, I wouldn't worry too much. These are now getting hard, but we'll take a look at the clues in the question that'll help you get into it. But first, I want to take a step back and take a look at kind of how divisibility works, because that's going to give us our clue to get into this question. Now, I'm going to at the same time work abstractly with algebra and go through some numbers so that you can see what's going on here. So if I wanted to divide a number a by another number b and represent that algebraically, what I would end up with is just some whole number. And because a might not be in the b times table, I might end up with the remainder. And we would write that as r over b as well. Now, multiplying both sides of this by b, we'd end up with a is equal to b times m plus r. Now, that might not make a huge amount of sense if you're just thinking about this algebraically. It might make more sense if I put some numbers to this. If I said a was 35 and b was going to be 4, then I could say 35 is 4 times 8, which will give me 32, plus 3. And now that 3, that's my remainder. That's how many I'd have left over. Or dividing both sides of this by 4, I'd have 35 over 4 is equal to 8 plus 3 over 4. Now, you might wonder where I'm going with this, but this setup is very close to how the question looks. Okay, x over y is 53.48, and we could separate that. X over y is equal to 53 plus, and I could rewrite that decimal as 48 over 100. Or in other words, I've got this arrangement, a over b, where x over y is equal to some whole number, the 53, plus the remainder, how many I had left over, divided by b, or in this case, divided by y. Now, I've got a remainder in the question. There are 12 oranges left over. So my remainder divided by what I'm dividing by, my remainder divided by, in this case, y, 12 divided by y, well, that's equal to the bit left over, 48 over 100. Now, in this case, all I've got to do is make the, well, I've got 48. I know that 12 and 48 are in a similar times table. If I divide this right-hand side, top and bottom, divide them by 4, I'd end up with 12 over 25. Because the top of these fractions are the same, well, the bottom of them are going to have to be the same as well for this equal sign to work. So that tells me y equals 25, and C is going to be my answer here. Now, that's one way of looking at this question. There are many others, but we'll give you one more just before we finish up today. I could just, starting from the beginning, x over y is 53.48. Or I could say that that is 5,348 divided by 100. Right, now it's just a case I'm going to start cancelling. So top and bottom divide by 2, and I'm going to get 2,674 over 50. Again, I've got a common factor of 2, top and bottom. I get 1,337 over 25. Now, you might be wondering where I'm going with this, but again, we come back to this idea that when we're doing a division, I could get some number of whole numbers. Now, 25 divides 100, 25 divides any multiple of 100, 25 divides 200, 25 divides 300, because 25 divides 100. That 1337 over 25, I could write that as 1300 over 25. That'll be a whole number, plus 37 over 25. But 37 over 25 is bigger than 1, so I could take out another 25 over 25, 1325 over 25, that'll still be a whole number, plus 12 over 25. Now, 12 over 25, this 12, again, that's our number of oranges left over. That's our remainder, which means the number that I must have been dividing by was the 25, which again confirms that our answer here should have been C. Two ways of looking at this question. Both ways are just as good as each other. If you had a different method that got you to the answer of 25, again, just as good. We're just looking for patterns and ways into these questions. Now, as I said at the beginning, as I've said throughout, it's very difficult to gauge the difficulty rating of a number properties question. So if you're in the high 40s and that question was a complete mystery, please don't panic. Once, as I hope you've seen throughout this video, once you spot the key to these questions, once you spot the way in, they can fall out very quickly. And hopefully we've given you a couple of keys to some of these questions. If, on the other hand, you're in the low 30s or in high 30s or low 40s and you're getting all of these right, then fantastic. Number properties is a strength for you, and I hope that we've helped you nudge that strength along a little bit more and you're able to unlock a couple more questions. Right, so as we've said, over the course of the two videos, number properties is a very big, broad topic with a couple of different things going on. You formalize the things you can formalize, but if you can spot the pattern throughout, that's going to be a huge help. Remember, as with all GMAT quant work, flexibility is the key here. And if you can develop a number of different methods and a number of different ways of looking at the questions, then you're in a very strong position. I hope that we've helped you out with some of that today, and we hope to see you back here again soon for more in our GMAT Ninja Quant series. Thank you very much. Have a good day, and we'll see you back here soon.